Hi guys, welcome to the last lecture of this course where we're gonna put everything we've learned together to look at PID or proportional integral derivative control and the Ziegler-Nichols method of designing PIDs. Once you put proportional, integral, and derivative control together, it becomes very hard to design an effective controller using analytical methods such as the ones we used in previous lectures when we used the second order characteristic equation s squared plus 2s times the damping coefficient times omega n plus omega n squared. Why? Simply because the transfer function of a system controlled using a PID can be of very high orders, and it also has at least three unknowns, so Kp, Ki, and Kd, or Kp, Ti, and Td in this particular case, and it becomes very difficult just to find it using typical mathematical equations. So what do we do in this case? We use empirical methods. Empirical methods are essentially trial and error methods, and we're going to look now at one of the most famous ones in PID design, the Ziegler-Nichols method. When Ziegler-Nichols created their PID control design method, they used the following system, represented in this block diagram. They started with the reference signal RT, to which was subtracted the output YT, and as you can see through the feedback transfer function HS equals 1, no particular operations were conducted on YT in the feedback. So RT minus YT gave the error ET. This was then passed through again Kp and then separated into three branches. First, again 1 over Ti to be followed by an integrator, one branch with nothing in it, a pure proportional control branch where just Kp was acting, and then a derivative branch with the gain Td followed by a differentiator. So as in any controller that we've seen previously, the sum of all these branches was then done to output a control signal ut, and finally this control signal was fed into the plant GPS to eventually give the output yt and repeat the cycle again. Here Kp is the proportional gain as usual, and proportional control increases with it. The greater Kp, the greater the proportional control. Ti is the integration time constant, and the bigger it is, the less the integral control. Ti is actually the inverse of the integral gain that we saw in the proportional plus integral control lectures. The bigger it is, the less the integral control. Td is the derivative time constant, and it is the same as the derivative gain that we saw in the proportional plus derivative lecture. The bigger it is, the greater the derivative control. From this, we can write that the transfer function of the controller which outputs the signal ut is equal to Kp multiplied by 1 plus 1 over Tis plus Tds. The Ziegler-Nichols rules allow to design proportional, proportional plus integral, or proportional plus integral plus derivative controllers. There are multiple sets of rules. We'll now look at the first one, rules based on the open loop plant reaction curve. So the open loop plant reaction curve is actually the response curve to an input to our open loop plant. Open loop plant means we just use the transfer function of our plant with no controller and with no feedback. Let's say we've input our T, our reference input, and measure the output yt, which is essentially the response. So what we want to do in this case is measure the step response to a step input with amplitude c and determine several characteristics of the transient. What I mean by amplitude c is that you can use any amplitude. All you gotta do is give it a step input. It means a sudden input of a fixed amplitude c, for example. So we want to determine multiple things from the response of the system yt. we want to measure the amplitude of that response with respect to time. First of all, we get the delay, D, the big capital D here, which is the delay in seconds it took for the system to output a response after which the step input was inputted. We also want the value tau in this case. So this value is very easy to measure. Let me just explain. So essentially, as you look at the response curve, it starts increasing faster and faster, and then its increasing will slow down to eventually go to a straight line at the value of A, the amplitude of the input. So what you want to do is you want to take the tangent of that curve at the point of inflection, which is the point at which the curve changes direction the most dramatically. So after it increases its maximum, it will start going back down to reach a straight line, and at that very point where you get the biggest change of direction, you want to take the tangent of the curve and measure the value in seconds between the intersection with the axis of zero amplitude, so more or less when the delay starts, to the intersection of that tangent with the line of amplitude A in this case. So this is the value tau. It is that measurement of the time that elapsed between the intersection of the tangent of the response curve with the line of zero amplitude and the line of amplitude A or C in this case. This allows us to set the variable R, which is equal to the amplitude A or C divided by the measurement tau. It is very important to note as well that the plant has to be stable. Otherwise, you will never be able to measure these values. You can see these values only work in the case of a stable response. Once you have this data, the design rules are the following. If you're designing a proportional controller, Kp is equal to C, or your amplitude A, divided by Rd. Ti is infinite because you want the integral control to be 0, and Td is 0 because you want your derivative control to be 0. If you're designing a proportional integral controller, then Kp is equal to 0.9 C divided by Rd. Ti is equal to 3.3 D. Remember that Ti is the inverse of the integral constant Ki, and Td is equal to 0 because we still don't have any derivative control. Finally, if we're designing a PID controller, then Kp is equal to 1.2 C divided by Rd, Ti is equal to 2D, and Td is equal to D over 2. Let's look at a second set of rules from the Ziegler-Nichols method based on the marginal stability of proportional control. So the first step is to implement only a proportional controller. As you can see from the block diagram we have here, we are talking about a very simple loop where we have, as usual, our input signal RT, to which we subtract the output of the system YT. This gives us the error ET that we feed into an integral gain Kp. This computes the control signal that we then feed into the plant GPS, and eventually it outputs YT again. So this is a very basic proportional control loop. And what we want to do in a second step is, for the same step input, we want to increase the value of Kp until the response of the system YT is about to become unstable. So to be very clear, unstable does not mean there are oscillations. Unstable means that the amplitude of the oscillations are increasing with time towards infinity. We call the resulting gain Kp star and the period of oscillation Tp star. So to make you understand exactly what I mean here is that the aim is to have a Kp star, and with respect to that Kp star, if Kp is inferior to it, then there are no oscillations in the system. It is completely stable and follows the step input that you want to have. If Kp is equal to Kp star, we have oscillations of period Tp star that oscillate with constant amplitude. So it's the exact point at which they are about to become unstable. So exactly between them decaying to a constant signal to them increasing in amplitude towards infinity. And finally, if Kp is superior to Kp stars, this means that the amplitude of the oscillation of our response are increased to infinity, so the response becomes unstable. Once we have a value for Kp star, so where Kp star is the value of Kp where the response is about to become unstable, so the oscillations are not varying in amplitude with time, then we can do the following. If we want a pure proportional controller, then we can set Kp to be equal to half of Kp star, and we have Ti equals infinity and Td equals 0. If we want a proportional plus integral Pi controller, then we set Kp equals 0.45 Kp star and Ti equals Tp star divided by 1.2. So Tp star again is the period of oscillation when the system is about to become unstable. In this case as well, because we have no derivative control, Td is equal to 0. Finally, for a proportional plus integral plus derivative controller, a PID control system, we want Kp to be equal to 0.6 Kp star, Ti to be equal to Tp star divided by 2, and finally Td to be equal to Tp star divided by 8. It is very important to note that the empirical Ziegler-Nichols method isn't an absolute answer to controller design. In some cases, you might get very lucky and get excellent responses from using it, but in most cases, the gains you obtain can be widely improved in order to get you the response you want exactly. So in my opinion, it's better as a very good first guess. Once you get your gains, you can tune them around to get the exact response you want. So the advantages of the Ziegler-Nichols method are that it is widely used, very famous, a lot of people will be able to help you with it if you decide to use it, and forums and other platforms probably give a lot of little tricks and tweaks that you can use to make it even better. There is no plant function required. It is a purely empirical method. All you need to do is input your reference signal, measure the output response, get the values from it, and then keep the same input but change your gains, and then observe the new response, and so on until you get exactly what you want. There is no closed loop design required. You don't need to have complicated transfer functions and study characteristic equations. All you need to do is trial and error. The disadvantages are that it can give poor results in some cases. As I just said, it can be widely optimized in these cases just by tuning it a bit differently, so it still works well as a first guess. And finally, the PID configuration that we showed in the first slide actually introduces 2 zeros in the transfer function of the system and can give a big overshoot. But the Ziegler-Nichols method was designed using it, so if you want the best results using the Ziegler-Nichols method, you're going to have to base your system on that PID configuration that we presented in the first slide. Okay guys, so this concludes the course. If I did everything right, you should now have the tools to design your own controller, from a simple proportional one to a full-on PID controller. So I just gave you here a block diagram of a more conventional PID controller than what we saw in the first slide of this lecture, the one used for the Ziegler-Nichols method. As you can see, it is a conventional closed-loop system with the reference and the output building the error. And then we have three clearly delimited branches, one for proportional control, KP, one for derivative control, and one for integral control. They are then summed into a control signal, which is then fed into a plant. So in the end, as you saw through the course, it all depends on your plant, okay? Depending on the system you're trying to control, you can use many different gains can work. You can have different configurations for different types of responses, so just PI sometimes, just PD sometimes. Sometimes you might need a full PID. Sometimes you can just put the derivative in the feedback of the control loop. Basically, the world is yours, and I strongly advise when you have a system that you want to control to try many different solutions. Think a bit about the response, how you want to improve it. For example, if you want less oscillations, maybe you got to dampen the response, so add a derivative somewhere. If you want to get rid of a steady state error, then you might need an integral controller. Think about it this way and try many different things, and you'll be able to create truly effective control systems. I will later on create other courses on how to actually implement this kind of control systems into actual microcontrollers using C. I will also do a course on how to create controller models in MATLAB and Simulink. This will all come later on, and I will keep you updated on this course. You will of course get some for free and very preferential rates. So I hope you like the course. If you have any questions, please do not hesitate to message me. I'm always available to help you understand some concepts or even help you with some of your projects if you're struggling. I love doing this, so keep me in the loop, guys. Thank you very much for supporting this course and following it. I wish you all the best.